you all have seen it before. Also, just come on, videos, people. Okay, so I will still introduce it from the start for anyone who has not seen. But for those who have seen it before, I'll give a couple of buffer problems per se. Okay, so first buffer problem, this is called error. I might get to this at some point, but even if I don't get to it, this is still a very nice result. So it says, okay, have any of you seen this name before?
Wait, what's written there?
Edda Shekeres.
I think I have, but I don't remember the statement exactly.
Okay, so given n square number, a list of n square numbers, a sequence. N square number. There's an n length subsequence, which is monotonic. This is for people who have seen things before and want to, like when I start from the right, from the basics, they want to not pay attention for some time, so they can try these problems. Yes, I'll give 2-3 problems. So, and even if you've seen, you can try to prove it again if you don't remember the proof. N square is fine. It looks cleaner. If you can do it with n minus n square plus 1, that's okay. The point remains the same. Okay, then there's this result of Edosh. This is quite tricky. Given a set of n real numbers.
Actually, in your screen, there is nothing coming written on it. Actually.
Oh, is this issue for everyone?
No, I can see.
Okay, I rejoin again.
Okay.
Oh,
Given a
also the
set of
first
n
problem.
real numbers, there's an n by 3.
What you have to prove in the first problem?
If you have any n square sequence, there are n of them, like an n size sequence, subsequence, which is monotonic, like completely increasing or completely decreasing.
Okay.
Let's say n
I
square
think
distinct.
it is n square plus 1, right?
N square is okay. N square is okay. There's an given a set of n real numbers, there is an n by 3, some free set, size, some free set. What does that mean? Some free set. All that means is they do not exist x, y, z such that x plus y is equal to c. Also, those of you who have not seen Pigeonhole before or are not very comfortable with it, don't worry about any of this. This is just for experienced people who don't want to listen to what I have to say. Okay. Are these 2 problems enough? You can try this with integers and then reals.
It is floor, right? There. In n by 3.
Sure. Keep it floor. I just said keep it floor. Doesn't matter. Okay. So if you've not seen either of these, I think it's okay. Given a set of n real numbers or n integers, there's an n by 3 size sum free set. So a sum free set is just a set in which there are no x, y, and z, such that x plus y is equal to z. Monotonic is just completely increasing or completely decreasing. All right. Anyone who wants to copy these down or take a screenshot, just do it now. Then I'll move on to the actual lecture. Okay, cool. So I'll start now. PHP. Okay, so what is Pigeonhole Principle or PHP? All it says is that if you have, let's say, n things you have, and you have k. Okay, let's not go with n things. Let's go with n pigeons. And you have k holes. Now, if you try to stuff these pigeons into these holes and you stuff all of them into some hole, then exists a hole with at least n by k pigeons. And exists a hole with at most n by k pigeons. Is the statement okay?
Yes.
Wait, what does it mean by at most floor function and by k pigeons? Isn't it, I understood the first one, but not the other.
Like there is also a hole that does not have that too many pigeons. Like if you have 3 pigeons to put in 2 holes, there is also a hole which has at most 1 pigeon, right?
Oh yeah, okay.
So these are the 2 parts. So can anyone sketch a proof for these? Or like, does everyone understand what this is trying to tell you?
Yes.
Yeah.
Sure. Okay. So if everyone gets what it's trying to tell you, yeah, go ahead, Ran.
So we first proved like the first part. So suppose there doesn't exist any hole with at least ceiling of n by k pigeons. So in any hole there are at max ceiling n by k minus 1 pigeons.
No, suppose every hole has that. Ceiling n by k minus 1 pigeon.
And
Okay.
now there are number of holes is k holes. So the maximum number of pigeons which can be k times this number.
Is at most
K times
n by k minus 1. Okay.
Yeah, and this like ceiling of n by k thing is
Ceiling of n by k is less than
n plus 1 by k, I guess.
n by k plus 1.
Yeah. So now
So
multiply this.
Implies less than n pigeon.
Yeah.
Good. Is this okay for everyone?
Could you explain again? Yes.
Okay, so we just a second. Right, sorry. Yeah, so what we started by saying, like do you get the actual statement of the theorem or the principle?
Yes, yes, yes.
Okay, so now what we say is, like for the sake of contradiction, assume like there's no hole with this many pigeons. So every hole has at most floor of n by k minus 1, a ceiling of n by k minus 1 pigeons, right?
Okay.
like if you can't have at least a, so you have to have at most a minus 1, right? Like no hole with at least a, so all holes have at most a minus 1.
Yes.
So if all holes have at most a minus 1, there are at most k into ceiling of n by k minus 1 pigeons.
Yes, yes, yes.
But that value is less than n. But we initially had n pigeons, which is a contradiction.
Okay.
So you can do the exact same thing on the other side. You can argue. Vansh, can you try arguing for the other side?
Okay.
Okay, so how did we start the last
I
proof?
just had a doubt. What is FTSOC?
For the sake of contradiction.
Oh, okay.
Vansh, how did we start?
Assuming that there was no hole.
Okay, so for the sake of contradiction, assume no such hole.
Yeah.
So what can we say if there's no such hole? How many pigeons in every hole?
Floor of n by k plus 1.
Yes.
Okay. Yes.
Yes, yes.
Okay, so how many total pigeons are there at least?
K into floor of n by k plus.
Good. But this is greater than n, you can check,
Yes.
which is a contradiction. We're saying at least this many pigeons are there, but we know there are total n pigeons. So this is the statement of PHP, the finite version that we care about now. We'll look at 2-3 examples and then I'll tell you what the infinite version is. Okay?
Yes.
Okay. Example. So let's look at the example that is the most common. You have 101 numbers, integers. A1, A2, dot, 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 A100. Exists I comma j such that 100 divides.
That must be till A101, right?
Yeah, sorry. Such that 100 divides AI minus aj. So how do we do this?
So since there are 101 integers, so since it's mod 100, the utmost number of remainders can only be 100. So then anyway there are 101. So basically there'll be one with an extra. Like worst case scenario, there'll be like two numbers with the same remainder mod 100. So yeah.
Good. So what Meenakshi said is you can look at it as what the remainder is left when you divide the number by 100. So since there are only 100 possibilities of the remainder, that is 0, 1, 2, 99, and there are two numbers which leave the same remainder. Let AI and AJ leave same remainder. by PHP. Then 100 divides Ci minus Aj. Okay. So this is the first example. Is this clear to everyone?
Yes.
Vansh, are you comfortable?
Yes, yes, yes.
Okay, good. So let us look at a trickier example. You have n plus 1 numbers from 1 to 2n. Or if you want concrete, 100 numbers, 101 numbers from 1 to 200. Prove that exist. Let's say A is the set. A comma B in A such that A divides B. Like if you have 100 in a set, if you have 101 numbers from 1 to 200, then there will be two numbers that divide one another. Like one of them divides the other. So this is the question. For those who have seen this before.
So, wait, can I tell the answer?
Have you seen it before?
No, but I think I know like how to do it.
Sure, go ahead.
So, so since we're taking n plus 1 numbers out of 2n numbers totally, like continuous, so if a number has to divide the other one, it has to at least be divisible by 2. So like if x has to divide y, the least it has to be is x is equal to 2y. So,
Okay.
so since there are n plus 1 numbers, definitely there'll be like, because there's more than just half of the entire thing, there's definitely one number that is going to be like, so when you take n plus 1 random numbers, there's definitely going to be one extra, which is going to, like at worst case scenario, at least one will be there such that it will be like double of the other or half of the other or vice versa.
That is, try that. Is that necessary? Like, for example, if
So
I
A
take
and
the...
B are not A and B are not the same, right?
Yes, of course.
Yeah.
Okay, so Meenakshi, for example, if I take the numbers from 102 to 200, and then I take the numbers 1 and 5, there are no two numbers which divide one another by 2, right?
No, but 2 is like minimum. I was just like giving an example because see, since
Yeah, but how do you do it concretely is the question. Like, it feels like this should work, but it's not concrete, right?
but so I took 2 because it'll be like worst case scenario.
How do you characterize what a worst case scenario is?
No, so see, if so totally there are 2n numbers. So when we're taking n plus 1, there'll be one that is like a. Oh wait, I'm not sure.
It's okay, take your time. No need to rush. Man, go on. Have you seen this before?
Wait, can we
No.
like divide it into two sets of odd and even numbers and somehow work out?
How would that work?
So like,
Let me just give another question for a minute, then we can discuss, okay? The third question is, you have 13 points on plane such that all have integer coordinates. There are 4 of them. With centroid, also integer coordinates. By centroid, I just mean the average of the coordinates, 4. Just add the coordinates and divide by 4. Right? Integer coordinates. Okay, go on.
I have idea for P2.
Okay.
So like we consider the number of pairs such that one divides the other. Like we count the number of pairs.
Okay. How do you count this? This sounds very hard.
Like so the number of pairs is just floor of n by 1 plus floor of n by 2 plus.
That is too complicated. It's too complicated.
But like if we show that floor thing is, I mean, something greater than 100, we done.
That if you can show that the number of such pairs is more than 100, no, that is not enough.
No, wait. Yeah, no.
Wait, we can use the fact that if A divides B, A is at least half, B is at least twice of A.
Okay, how do you use that?
Yeah, so what I said earlier, so B is at least twice of A, right? So we need from this set, we need to pick 101 numbers such that one number is at least twice of the other. So
No. I'm telling you that given any 101 numbers, you can find 2 which divide one another.
Yeah.
Like I'm giving you 101 of my choice. But then you say no, I can still find 2 numbers.
Yeah, no, that's what I'm saying. So we need to find like one number that is like at least twice of another number in the same set of 101 numbers. Okay. So for the worst case scenario, we can take like 100 numbers. I mean, yeah. So we'll first we'll take the last one later. So 100 numbers, we'll take them continuously at a stretch. So for example, if we take from 1 to 100, or we can take 101 to 200. So 101 is still, so 200 is like double of 100. So anyway, we need to take a number less than that. So when we take a number less than that, like suppose like from something from 1 to 100, then one of them, it will definitely, the double of that is definitely going to be in the 100 numbers that we already chose.
Not necessarily, right? I could just pick the number 3.
Excuse me,
oh,
can I
yeah.
suggest something?
Yeah, go on, Ishan.
Yeah, like we can create a pair such that one is double the other. So there should be n such pairs, right?
Not necessarily. Like there are n such
like
pairs.
we can choose 1, 2 is one pair, 2, 4 is another pair. So there will be n pairs, right?
But the thing is, there are also n by 2 more numbers that you have not considered, the odd numbers between n plus 1 and 2n.
No, I'm saying like 1, 2 is a pair, 2, 4 is another pair, 3, 6 is another pair. So there will be n pairs, right?
Yes.
And we are taking n plus 1 numbers, right?
Yes, but the thing is, I could also pick the number 2n minus 1, which is in none of these pairs. I could also pick the number 2n minus 3, which is in none of these pairs. Like any number from 101, like 101, 103, in case of this thing, is not in any of these pairs. So you can pick these also.
Okay.
But these are not 101 numbers. They are less, no?
Yeah, but like the point he was trying to do is that you can find n plus 1 of these, like n plus 1 from these pairs, so some 2 are from the same pair.
Yes.
But there are 2 issues. One is obviously this, and the thing is he's overcounting these pairs a lot. See, like 2 is in multiple pairs, 4 is in multiple pairs, and so on. Why would you ever want that?
I think I know P3.
Okay, go on.
So mod 2, these like you can have 0, 0, 1, 1, 0, 1, 1, 0.
Okay, 4 possibilities mod 2.
So then 13 by 4, you get 4 of them that are the same.
Okay.
And then 9, and then taking away those 4, you get 9. 9 by 4, you get 3 that are the same.
Sorry, you get 4 which have
Like the same thing mod 2.
Okay, taking
And
away these 4.
excluding those 4s, you the 9 by 4, you get 3 that are the same.
3 have same coordinates mod 2.
Split the 4 into 2 pairs, and then you'll get like 2 things that are both 0 mod 2 when you add them. Entirely 0, like 0, 0 when you add, after you add mod 2.
Okay, you can split it into 2 things and you get 2 pairs.
And so mod 4, there'll be 0, 0 or 2, 2. And then the other one also will get 1 pair like that. So there's 3 things and there's only 2 possibilities. So we have some 2 that are the same. Add those and you get the required thing.
Okay, so with this you get, okay, good. So with this and this, you get 3 pairs coming to 0 mod 2. So you have even coordinate, even coordinate, even coordinate, even coordinate, even coordinate, even coordinate, and you can divide it by, so there are only 2 versions that don't work, you're saying, right?
Yeah, they can only be 0, 0 or 2, 2.
0, 0 or 2, 2. Why
Or
not 2, 0?
Oh yeah, 2, 0. I forgot about 2, 0. Okay, just we have to keep doing from 9. Okay.
No, it's okay. You're very close. You created 2 such pairs, right?
We just need to keep going, right? From 9, we can go to 6. 6 by 4, you'll get.
Don't do 6. You have 7. You only take 2 of them, right?
Yeah, we have
only
7.
Take a pair. So from 7, you can find another 2. And from 5, you can find another 2.
Yeah, okay, then we're done.
So you get 5 pairs coming to 0.
Yeah.
Okay. So repeat. Yeah?
Yeah.
Okay, good. Does everyone understand what Siddharth did?
Yeah.
So what he's saying is, if you have like at least 5 things, then there are 2 of them which have the same coordinate pair if you look mod 2 only. If they're the same coordinate pair, you can take a pair of them and remove them. You get 1 pair. You can take another pair, 3rd pair, 4th pair, and a 5th pair. And you get 5 pairs, each of which has the same coordinates mod 2. So when you add these coordinates mod 2, you get an even coordinate, even coordinate, and then you can divide by 2. So you can replace each of these with a plus b by a1 plus a2 by 2. a3 plus b1 plus b2 by 2, let's say, and so on. And again, because of the same argument, 2 of these will have the same coordinates. So like a1 plus a2 by 2 is equal to, let's say, c1 plus c2 by 2 mod 2. So we can again add them and we'll get that a1 plus a2 plus c2 plus c1 plus c2 by 4 has integer coordinates. Okay, so that is the argument. Good. So now the other problem.
Sir, can I try the second one?
Yes, go ahead.
We have to choose. I am trying for 101 from 200.
Okay.
So I thought that if we choose 101 numbers from 200, at least 2 of them will have same remainder.
From? The remainder meaning? Remainder with respect to
mod 100.
Okay, 2 have same remainder mod 100.
Yes. So we can subtract that 2 numbers.
Okay.
The number which we get, let's suppose a1 and a2 has same remainder. So a1 minus a2 will be divisible by 100.
Okay.
So we can say that A1 minus A2 is a number which lies from 1 to 200.
But we don't need to have picked A1 minus A2, right? Like A1 minus A2 is a number, but it's not necessary that we have picked it.
But we can pick any two numbers. Like I have picked 199 and 200. So by not that, but I have chosen two numbers. Like
A1 and A2 belong to the set that we have picked.
Yes.
Yeah. But A1 minus A2 does not need to.
So 1 and 101. So by subtracting them, it is divisible by 100.
Yes, it must.
So it has to be 100 only.
Yes.
Yes,
sorry.
Yes, but the number A1 minus A2 divided by any number from the set will be divisible by it, na?
What?
If A1 minus A2 is 0 mod 100. So if any other number from the set we take, like let's suppose B1. So by dividing A1, the B1 has some remainder with mod 100.
B1 has some remainder mod 100. Okay.
So by dividing both of them, we can get 0 as a remainder mod 100.
You got a remainder mod 100 as 0, but like what use is that?
So from n plus the set of number 101 numbers, there will be two numbers which will have 0 mod 1 0 mod 100 remainders, and by taking any of the numbers from 101.
Not 0 mod 100. The difference is 0 mod 100. There's the same remainder.
The difference, yes. That A1 minus A2 is mod 100. 0 mod 100. I'm saying that
A1 minus A2 is in fact 100 because it can't be 0 and it can't be 200.
With Rohan, can I try a solution?
Yes. Just a second. Let Man complete once.
Yes, sure.
So I was actually trying to prove that if A1 minus A2 is 0 mod 100, then we can take any of the number from the set of 101 numbers and divide it by that. So they will always give as A1 minus A2 is a number from the set. So let's suppose it's
X. It's not A1 minus A2 is not necessarily in the set. Why is it in the set?
Okay. Yes. Okay.
Also, try a few cases by hand, like a small cases. Okay. Try for instead of numbers, 6 numbers from 1 to 10, or 5 numbers from 1 to 8, and once. Okay. Tuhin, go on.
Yes. So I was telling that we can take n sets such that to each of them we will give the odd numbers from 1 to 2n, because we can confirm that all the even numbers from 1 to 2n are somehow the multiples of the odd numbers, but the opposite isn't true. So we will take n sets such that the first set has the first odd number and all of its even multiples, and similarly the second set the second odd number and all its even multiples. So like that we can confirm that all of our 2n numbers are somehow in one of the n sets. So now to choose n plus 1 numbers, we have to take by PHP we have to take 2 of the numbers from any one set, and we know that if we take 2 numbers, then they are obviously one of them is the multiple of the other.
Perfect. That is the correct argument. Well done. So what he said is you label them with 1, 3, 5, 7 instead, just the odd numbers. While even you were looking at this idea, you don't need to consider 1, 2, and 2, 4 separately. You can just add 4 to the same list. Why does it need to be pairs? So from every odd number, you can try to generate a list of numbers. Now, because you have n plus 1 numbers being picked, some of those numbers must be from the same series, from the same set. If they're from this set, then obviously they're both multiples of 5 into 2 to the I and 5 into 2 to the j, which obviously divide one another, because the other is just 2 to the I minus j times the other.
But what if, like, let's say from this 5-10 set only, we pick 20 and 30?
How is 30 in this set?
It's a multiple of 5, no?
I'm not adding multiples of 5. I'm just adding all even
Like 5
multiples.
into 2, 5 into 4.
Yeah, fine. Then.
Okay. Just like the even multiples are in the set. Not even, like powers of 2. As yeah. Okay. So are the ideas clear? Or do you want one or two more examples? Okay, sure. I want to show this idea of partial sums. So let's try that. So again, let's say you have n plus 1 numbers, any n plus 1 numbers, a1, a2, an plus 1. Show that you can find I and j such that ai plus 1 plus dot 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 aj is divisible by n. Is it necessary n plus 1? I don't think so. Okay. Yeah. A1 to an, there exists I and j such that ai and okay, I less than equal to j.
There are n plus 1 numbers, तो n plus 1 तक होगा ना?
N into. Not n plus.
We can just consider like A1.
If you know the answer, just like, okay, for a moment. Okay, this is one problem to try. This is like the fourth problem, right?
So like I and j can be any numbers under n, right?
Yes, yes.
And ing can be equal also, right?
Yes.
Okay.
Yes. The other problem you can try is there exists k such that 1, 1, 1, 1 written k times is divisible by let's say 2020.
Wait, in that question is A1, A2, and so on consecutive integers?
No, just some n integers.
Oh.
So can we take
just a second? You know what the Fibonacci numbers are, right?
Yes.
Yeah.
F0 is equal to 1, F1 is equal to 1, Fn is equal to Fn minus 1 plus Fn minus 2. Okay. Exists k such that Fk has 2022 zeros at its end.
So like even if there are any random numbers, we can take consecutive also, right?
What do you mean?
Means
Like
we can
they're given to you.
True for consecutives also.
Yes, it could be. They could be consecutive. I've just not given you that information. I've just told you that there are some n numbers.
For the fifth problem, 111 k times it is just 10 to the power k minus 1 by 9, right?
Let's not use something like Fermat's little theorem or something.
Okay.
So can I try the fourth one?
Sure, go ahead.
We take as n numbers are there, so we can take uh, mod n of all the numbers.
Okay.
So if we take mod n of all the numbers, there are n minus one there are n zeros. There
What
are
do you mean? There are n
n means
zeros?
sorry n remainders. Sorry. I'm
Yes,
sorry.
there are n
There are n
remainders.
remainders. There are n
Okay.
remainders, and the remainders can be from 0 to n minus 1.
Yes.
So if you divide all the numbers by n and adding 0, or 0 is a 1, n minus 1, then 2 and n minus 2, they will cancel out. They will cancel out,
But it could be very far apart, right? I'm telling you that these are consecutive. Like I to j. It's not like you can just say the first number and the last number sum to something divisible by n. Do you get what I mean? It has to be some n consecutive number, like some series of consecutive numbers, like in the sequence, not actually consecutive, just consecutive in the sequence.
oh, okay.
I solved the fifth one. Shall I tell?
Sure.
So consider 24 numbers of this form.
Okay, so which ones?
Like just take any 1, 1, 1, 1, 1, 1. Oh no,
Okay.
wait. Yeah, fine. Yeah, pick any. And then two of these must be like same remainder modulo 2023.
Two with same remainder, not 2023.
Let's
Okay.
say one is like of A length and another is of B length, and A is greater than B.
Okay.
Now you subtract the first with the like A minus B. So it's a number of the form 1, 1, 1 A minus B times followed by some zeros.
And wait. B times?
A is greater than B, we assume.
A greater than B. Okay.
Subtract the second from the first.
Okay, so we get 1, 1, 1, 1.
A minus B times and zeros.
0.
This is divisible by 2023.
Divisible by 2023. Okay.
We cannot divide this first number by 10 to the power B because it's like 2 and 5 only, and 2023 is not divisible by 2 and 5.
Okay, but
so we get a number of 1, 1, 1, 1, 1, which is divisible by 2023 with A minus B ones.
10 to the B, 23 equal to 1. Thus, 2023 divided 1, 1, 1, A minus B times. Perfect. Good.
Also, was this problem for mathematical circles? Because I remember some exponent thing being there.
Oh, this is a very standard example. You'll find it everywhere.
I see.
Like you can switch it with 1, 1, 1 to 3, 3, 3, 2, 2, 2, 7, 7, 7. All of these exist. Okay, good.
Can you just repeat the fourth question, like what we have to do finally, like the AI plus AI plus 1 question?
Okay, so you just need to find, like I've given you some numbers. Let's take a concrete example. Like I give you 3 numbers, let's say 37, 21, and 4 in this sequence. Now you need to find some subsequence which is divisible by 3. So in this case, you can just say 21 alone. Works, right?
Yeah.
If this was 22, then you would have to say 37 plus 22 plus 4. If
So we
this
have
was
to know
20,
that there's at least one which is divisible by n.
yes, but if this was 23, you could have just done 37 plus 23. But what the point is, sorry, that let's say this is 5, then your answer is 37 plus 23. It is not 37 plus 5. 37 plus 5 is wrong just because they are not consecutive.
Okay.
So
want
this
to?
must be true even if the numbers are like the consecutive terms are also consecutive integers, right?
Yes, yes. There could be anything. We have no information.
But I found a counter example. Like if we take 1 to 6, all the consecutive integers,
Okay.
and for I is equal to 4, then
What do you
we
mean?
can't work
What?
out such that the sum will be
No, no, no.
divisible by 6.
Exist ing. What do you mean? There's just existence of ing, right?
Sorry, I got it wrong. Yes, yes.
You're just saying there exists some pair like ing such that if you take from I to j, it will work.
Okay, right. I thought like for all it's possible questions.
No, no, no. That is just wrong, right? Then I'm just basically disregarding some part of the sequence.
Um,
Go on to that.
If
I
we
think I
just
got the sixth one.
Can you tell of the sixth one?
Yeah, the sixth one.
Sure, go ahead.
Okay. Just consider like pairs of consecutive Fibonacci numbers. And then
The
like consider
pairs fi,
like a big number, like 2022 square or something, I think.
Okay.
2022 square plus 1, I guess.
What was the condition? I said 2022 zeros at the end. It's
Oh, okay. So then whatever okay, so 10 raised to 4044 plus 1.
You're just doing it for any mod n, right? Like
Yeah, for
you
any
will find
mod n,
okay.
n square plus 1 version.
Consider n square plus 1 such pairs. Okay.
Wait, I think I was wrong. 1 second.
We want some numbers here. Mod n.
No, I was wrong. I was wrong.
are A1 to AN unique or they can be same also?
They can be same.
Okay.
But it doesn't matter, right?
Yeah,
If
I
even
mean,
if I
yeah,
even if I just let me complete. Even if I impose the condition of unique, you could just say 3 and 3 plus n are there, which like completely loses the point of uniqueness, right?
yeah, it has to be like unique in mod terms only, then yeah, it matters.
Yeah, but that is unnecessary. We don't need that. Go ahead, Malik.
Yeah, so we consider the n numbers A1, A1 plus A2, A1 plus A2 plus A3, all up to A1 plus A2 plus all up to AN.
Good. Just let me write this. We call S0 the zeroth partial sum as 0. We call the first partial sum S1 as A1. Call the second partial sum as A1 plus A2, and so on. Okay. So let's say Sn is equal to A1 plus A2 plus A. These are what you're defining, right, Malik?
No, I defined it from A1, A1 plus A2 all up to A1 plus AN.
Yes, I just added a 0 for convenience.
Yeah, okay. So now these are n numbers, and if any one of them is divisible by n, then we are done because these are consecutive.
Yes.
So we assume the opposite, that none of them is divisible by n. So each of them can have remainder 1, 2, 3, all up to n minus 1 modulo n.
Yes.
There are n minus 1 possible remainders and n terms. So by Pigeonhole principle, some two must have the same remainder. Say a1 plus a2 plus all up to ax and a1 plus all up to ay have the same remainders with x greater than y. Then we consider ay plus 1 plus ay plus 2 all up to ax, and we are done.
Good. Okay.
Thank you.
So I'll just tell his argument. So what he did is, now you'll see why I addressed 0 for convenience. By pigeonhole principle, these are n plus 1 numbers. So two of them have the same remainder, mod n. Let's say Si and Sj with I greater than j. Leave same remainder. Implies ai plus 1 plus ai plus 2 plus aj is to the power n. sorry, j plus 1. A j plus 1 and we are done. Bale, do you see why S0 is useful? You don't have to do your initial argument.
Yeah, I got it. Thank you.
Yeah. Like your initial argument is covered by S0. That something is divisible by n. This idea of partial sums is very useful in general. Okay, Vansh, go ahead.
I am just a doubt.
Yeah.
Like Pigeonhole Principle says that there are n pigeons and then k holes.
Oh, n plus 1 pigeons, no? S0,
Yeah.
S1, S2, Sn. There are n plus 1 things. So n plus 1 pigeons and n holes.
Yeah.
Sure? Okay. Okay, so this works. Let us try the Fibonacci idea now. That is one last problem, and hopefully we'll have about half an hour and we can see something cool. We'll have to make a choice for that time. Yeah, any ideas for the Fibonacci thing?
Is it just this, like, if you have two tuples that are the same, then you can just keep adding and then it's like periodic, but then what after?
You can do the reverse direction is the point. Don't add. Why would you add? You know
okay.
a place. Yeah, got it?
Okay, you go back. Okay.
Okay, so tell the solution.
Okay, if you have some n square plus 1 and some two are, if some two are equal, then you can...
Mod n.
Yeah, congruent mod n. Then you,
Fi
you can...
comma f.
Yeah.
Congruent to fj comma mod n.
Then you can keep subtracting from the left. Okay. Keep going left. So like fi minus 1 is congruent to fj minus 1. And then keep going until you get to 1, 1.
Congruent to fj minus 1 comma fj, because we did the subtraction, and you can keep going till you get f0 comma f1 is congruent to fj minus I, fj minus I plus 1, and then you can go one step further back and you'll get 0 is congruent to fj minus I plus 1 minus 1 mod n.
How did you do the last step?
Oh, this is just 1 comma 1. Both are 1 mod n. Oh.
I will take f0. Okay.
Yeah, f0 is 1.
Oh, also, like for this problem, I was like just seeing the Fibonacci numbers from 0 to 200 so as to get some nice property. There was this nice property that every 15th Fibonacci number is divisible by 10.
Every 15th, you said.
Like f of 0 is 0 and f of 1 is what?
Are you sure it's 15?
Yeah, like f of 0 is 0, f of 1 is 1, f of 2 is 1.
Yeah.
Then f of 15 is divisible by 10.
Interesting. I would have not expect. I thought it was probably. Let me think. 15. Huh?
610.
Is it not 16? I would have guessed it would be 16 or something like that.
No. Like if you take f of 1 as like f of 0 is 1, then it
okay. I don't remember exactly, but I'll tell you some property if you're curious. You know Binet's formula?
Yeah.
So try to use that and mod any prime. Try to find something that works.
Okay.
Is it
So
actually the every 16th number divisible by 10?
Yeah, that's what I would have expected.
Because 16th one is 610. So
That's what I would have expected, that it's 16th number, not.
Like the one which is here is F0 is 0, not 1. It's according.
Right. Okay. So maybe 4 square minus 1, I don't know. It must be p
So
square
if you
minus.
see from 0, then F15th is the 16th term only.
Yeah, that is okay.
Yeah.
Okay, it must be 4 square minus 1 is the connection, I think. Like in general, p square minus 1, I think, is always a period. So for any prime. Like you can always find beta periods, so I'll talk about it at some point. Let me know if you want to discuss it at some point. Okay. Are these examples clear?
yes.
What are you saying, Atman?
I was sort of giving an add-on for P4. We try to construct a number of that form where the digits can only be 1 and 0, right? So I'm saying try that with general digits A and B.
You mean to this problem?
Yes, the one where you have to find number with only ones and zeros.
With number of ones only. Yeah, sure. Yeah, okay, cool. All right, at this point, I would need you to make a choice. We have 2 paths to go down. Okay, 3, let's say. One is just more problems. We only have about half an hour, so something called Ramsey numbers. Third is number theory and approximating rationals, irrationals. All of these are nice things. Just pick.
In NP part, is it like that idea 3.14141? That continued fraction idea which we discussed yesterday in that lecture of stems. Is it that thing?
Continued fractions? I never
like
discussed continued.
No. Professor actually discussed. No, is it the same thing as that?
Oh, we'll not, that works, but we'll use some other method. Like that had nothing to do with PHP, right?
Yes.
Okay, let's see what the opinion is in the chat. 2 or 3, 3. No problems. I need that's done. Ramsey 2. Okay, can we create a poll? Is that even a thing?
Yeah, there is an option though.
Okay, let's go with Ramsey. A lot of people seem to insist on Ramsey. Cool. Yeah, I mean, most people are going with 2 only. That's okay. Huh, text size changed. Interesting. I have no idea how. All right. So first thing, you must have heard of this friendship theorem. Have you heard of it?
No.
I have
So
heard
if
of it.
okay, you have 6 people. Every pair is some friends or not friends. Every pair of people can be friends or they can be enemies, let's say. Friends or enemies. Prove that there are three who are mutual friends or enemies, mutual enemies.
So actually, any two of them are friends.
Any two of them could be friends, or any two of them could be enemies. Like you and I could be friends, or you and I could be enemies. That's like there's nothing in between. It's a very binary thing. You are just like get along or hate each other.
I have seen this earlier. Shall I speak or shall I?
No, okay, try this. You have like this is how do you think of this? You can think of it as you have 6 points on the plane and you connect them with like black or red lines, right? And
Yes.
there's a black triangle or a red
Triangle.
triangle.
Yeah.
Okay. So I instead of 6 points, I make it an octagon.
Okay.
I make it 8 points. Okay. Show that there are 7 triangles which are of the same color. Like not all of them same color, like 7 just completely black or completely red or completely blue.
Wait, what does a color stand for?
Oh, here it's not relevant. Like Pranav just want another problem. I gave him another problem. Don't worry about it.
Actually, I've seen this too, but I don't remember. So.
I see.
Also, what does it mean by mutual friends or mutual enemies?
Like if you can find 3 people who are all friends of each other or like who are all enemies of each other.
Oh.
And you can in fact show that you can find 2 such triangles. Instead of, I'm just asking you to find 1 such triangle, but in fact there are at least 2 such triangles always.
So can we start with a set with one means a person A and B? They are both enemies of each other.
Okay. Mayuk, have you done the other part also? That instead of 6, if I update it to 8 people and ask you for 7 triangles instead of just 1 triangle. Right, mutual enemies. Okay, then try that. Man, go on.
So I was saying that we can try say that first two people are there A and B. They are enemies of mutual enemies of each other.
Okay.
Actually, I also want to ask that is that necessity there? There should be a friendship between two.
Some people could be friends, some people could not be friends. We don't know.
Oh, okay. So we are left with 4 other peoples. 4 other people.
Okay.
So at least two of at least A is enemy with B, but A could be friend or enemy with any of the 4.
Sure.
So if A is enemy with any of it, then we are done. That 3 are mutual enemies.
No. You also need that B to be enemy of that person if you are finding another person.
Okay. So okay.
Yeah.
I have a double counting proof of the octagon one. Should I search for a PHP one?
No. Double counting is perfect.
Okay.
Do you remember the Edos-Shekares and the Edos problem from the beginning?
Oh yeah, I've written down. Yeah, I'll just go.
Yeah, just try those. Or instead, you can have you seen this friendship theorem result?
Yeah, they're both the same argument, I think. The 8 and the 6.
Okay, so can you count it with 17 people and they could have 3 types of relationships instead of 2, like friends or mutual enemies, right? They could be friends, enemies, or don't know each other.
And then what is the bound?
17.
No,
You just need 17 people are there. Any two could know each other, like could be friends, could be enemies, or not know each other. Triangle with the same property.
How many triangles?
Just one.
Okay, one.
So we can make an argument that A is enemy with all other 5 people.
You can.
If
But why is it necessary? A could be friends with some people as well, right?
yeah, it could be friends or enemies. At least 2. A is enemy or friend with at least 2.
Is it at least 2, or can you do better than 2? There
yes,
are 5
better
other
than
people.
2 also. Yes, A can be enemy with 2, 3, 4, or 5, or friends with 2, 3, or 4 or 5.
That is okay, but what are you trying to argue? What is your argument? That you have a person A, and now you have 5 people. So you're saying at least 2 of them are his friends, or 2 of them are his enemies, right?
Yes.
But why are you saying 2 is my question. Can you not say 3?
They can be 3.
But
There
if you can
can be
say
3,
3,
but
if you can say, can't you guarantee that there are 3 is my question. By Pigeonhole Principle, there are 5 people. So at least 3 are in the same category, right?
yes.
Okay. So let's say these are the 3 people. I'll just draw a red edge to them.
And among those 3, there are. We can also say that there are 3. Among those 3, there are 2 people with same polarity. So it's
polarity. What?
We can't. I mean, like they're the same category. So among those 3, there'll be 2 people who are either friends or enemies.
I mean, can these 2 people be enemies? Like A is enemy to all 3 of these. Can A be enemy? Like, can these 2 be enemy now?
No. Okay. Wait. No. But so among those 3, there'll be 2 people who are like a same category, like mutually.
Like they're friends with another. Why? Or like they're enemies with another. What are you trying to argue?
No. So basically, suppose A is friends with the first 3 people. Then among those 3 people, there'll be 2 people who are friends with each other.
Why?
Pigeonhole principle, right?
How?
Oh wait, they can also be enemies.
Yes.
Yeah.
The point is, if these are enemy pairs, like let's say C, D, and E, that A is enemy of C, A is enemy of D, and A is enemy of E, then D and E can't be enemies because then we'll get a triangle. Similarly, C and D can't be enemies because again we'll get a triangle. And C and E can't be enemies because we'll get a triangle, but then CDE is a triangle.
So we prove by contradiction that there are no 3 pairs such as mutual friends or mutual enemies. Then we say that. Then we prove that at least one person has 3 people with whom it will be enemy or a friend, and then with the mutual the mutual interest relation between the 2 other will also create a triangle. So
yes, that is precisely what we did.
Okay.
Yes, we can guarantee in fact 2 triangles, Pranav. But I'll not get into that. Okay, so you could think of this as initially, instead of thinking of the problem in terms of friends or things like that, we could say that we have 6 points and we connect every two points with a red color if they are friends and a blue color if they are, like, let's say we use green color if they're friends. So there is a triangle which has all 3 sides of the same color. Yes. So in fact, why do we only need to consider 2 colors? We can try 3 colors. We can try 4 colors.
But you can only be friends or not friends, right?
I mean, you could Like I'm just saying, like you don't need to stay in the friends not friends structure. You can just instead of thinking, you can just start thinking of as some points, each point pair connected with some color, and then how many like some sequence of colors you have and a lot of points you have. Okay. So now the big result at the end of all this is like currently we were demanding triangles where like 3 people are mutually friends or something like that. We could have demanded four people who are all mutually friends. We could have demanded 5 people who are all mutually friends, and so on, right? But then we'll have to bloat up the number 6. We only demanded the number 6. We'll have to bloat it up. So the big result at the end of all this is that if you have, let's say, color 1, color 2, color n, and for the color 1, you want A1 people who are all friends with each other, or like who have like A1 set of people who have all just color 1 between them. With color 2, you want A2 people. With color n, you want an people. Like if any of these conditions are satisfied, you're happy. If you can find A1 people with all color 1 between them, or A2 people with all color 2 between them, or something like this, and then you're very happy. Okay. So the big result is that if this is the condition you have, then there is a number n, such that if you have n people and each pair colored with these colors, at least one of these conditions is satisfied.
Can you repeat this condition? Like what's A1, A2, AN here?
Like currently we were demanding triangles, right? That
yes,
3 people who mutually have the same color. We could have demanded 4 people who have just like all color 1. We could have demanded 5 people. So with color 1, we are demanding A1 people. Like right now we demanded red also 3 triangle and green also triangle, right? With red, we could have demanded like either give me a red quadrilateral or give me a green triangle. We could have made that a demand as well.
Yeah.
So we can say color 1, color 2, A2 people.
So if we make a quadrilateral, then not all of them will be mutually connected, right? So for example, so
like you could you want this condition that all these 6 things are of the same color.
Yeah.
So with color n, you want an people, and so on. So if this is the condition you want, there is a large enough n that if you have n people, this large enough, let's say n is confusing, let's say if you have this large enough m, that if you have m people, then at least one of these colors has like its respective size shape that you want. Yeah. This is the huge result, and all of it will follow by PHP. And you can in fact give bounds on it, on what size it will be. Horrible bounds, no doubt. You can't find very good bounds, but you can bound it and you can find good things using PHP.
Bounds on n?
Bounds on n.
Also,
that is where I'll leave you.
Is there like some result which states that if m is infinite, you cannot find such pairing?
Is there such a result such as?
If m is infinite, you cannot find. Because
I mean, just consider a large enough subset of those people, right?
Yeah, fine, but like the infinite hall doesn't work, no, for this reason.
What do you mean?
It seems relatable to that.
I don't get what you're trying to say. I mean,
like the Hall's theorem work for finite bipartite graphs, right?
Okay.
But it doesn't work for infinite graph. There was some problem.
What does? Sure, because that has no meaning.
What do you mean by no meaning? I mean,
like that doesn't leave it. Okay, that is not the point. This has nothing to do with that, right? Like if you have infinite colors, then the problem starts making no sense at all. Just because if you have infinite colors, you could just give everyone a unique color, like every pair a unique color.
No, my question was infinite m, not the colors.
I mean, infinite m, if you have just conditions, are just still finite, right? And
Yeah, okay.
if I've claimed there is an m which works, then I can just consider some m people and work only on them.
Fine. I found the fault which I was missing. Yeah, okay.
This is the big result. Even if this does not make sense, it's okay. This is just a fancy thing I wanted to tell you for no good reason. But yeah, this is a very nice result. And it is inspired from this thing, just because of this interpretation of the problem. Oh, these are called Ramsey numbers, the respective m you'll get. This will be called, yeah, R of A1, A2, AN.
Wait, what is the Ramsey number in this?
The at least what number of people do you need to have this condition satisfied?
Oh, okay.
Like we can say our Ramsey of 3, 3 is equal to 6.
Oh, okay, yeah.
That either we have a red triangle or a blue triangle. Yeah.
So the octahedron you can find 8 triangles, right?
Perhaps. I don't remember the exact count.
Also for the 17 thing, like you can't, like it doesn't fall to just straight double counting, right? You need more.
Oh. Just like from the first person, there are 6 of the same color. And you can't have this color repeated here. And then friendship.
Oh, okay. That's much better.
Yeah, 17 then goes to what? If you replace, like currently you did it with 17, I think 87? Or I don't know. You can just keep extending this.
Okay.
Oh, not 87.
Like whatever number, but with 4 colors, and then you keep going.
Yeah. Just okay. Not 87. This is just I can't multiply and all those. So it's too fancy. 16 into 4. I think 66. Right? 66 makes sense. 60.
Yeah.
And then 327 you can do it with if you want like 5 colors and so on. Just 6 colors. 5. Yeah, you know what you mean. You know what I mean.
Yeah.
This is 4 colors and this is 5 colors. Yay. I can do addition and all. Right. That is the content for today. Oh no, today's class didn't go so well. It's only 16 people today.
So, like so is there a formula or something to like find?
That is an interesting thing. We have bounds, but they're horrible bounds.
Okay.
Like we have no good bounds on. Like I think even R4 is not known. Like for even R4, I don't think a good bound is known.
But isn't there some recurrence with Ramsey numbers? I don't exactly.
Those are upper bounds. Those are horrible upper bounds.
Why do you need upper bound on this? Like any m greater than that, smaller thing works, no?
Yeah, but like so, like what is that at least value? At least like what is that value at least, right?
Yeah,
like what is the minimum number that you're happy with? So we don't know what minimum number we are happy with. We have like good bounds, like at least like this number is always sufficient, we know. But below that, we have to start getting no idea at all. Just because without PHP and such arguments, this is hard to compute. There is no good way to compute it. And otherwise, it's case bash, which is too large. There are too many colorings. Like even if you have just 20 points, right, and you have 3 colors, that's okay. Let's say you have 100 points and you have 2 colors. That's 2 to the 100. I think that's like more than atoms than in the universe, right? Something like that.
Wouldn't it be 2 to the power 100 choose to number of edges of possibilities?
Yes, 2 to the 100 choose to. Okay, so it gets started. It gets you can't do it with coloring even in let's say 15 points. Even that is what 2 to the 105. That's more that's more than the number of atoms in the universe. You can't do that.
Also, many people left up the first problem. I think they thought it will be very basic. So that's it.
That's why I gave buffers, but okay.
Should I end the recording?
Yeah, of course. Sorry if this was too boring.